To my YouTube channel. So here today we are going to be looking at Kepler's third law and all the calculations. So what does it say? So Kepler's third law states that the square of the orbital period is directly proportional to the cube of the radius. So this is Kepler's third law. The square of the orbital period is directly proportional to the cube of the radius. So the expression is this. Now, we might be required to derive this formula as an exam question. So we need to derive it before we look at all these questions. So these questions are common, but they won't ask you to say using Kepler's third law. No, you will just have to be able to tell. So now, how do we come up with a formula? Or rather, how do we prove that the square of the period is directly proportional to the cube of the radius? So this is what we are going to do. So let's say we have here, so as you can see, we have the centripetal force. Centripetal force wants these objects to go to the center like that. Then we also have the mass of the bigger object, which is in this case the sun. So this is the assumption. Assume that the earth is orbiting the sun. So that means to say it's passing through its orbit like that. Now what we begin to do is that if that is the case, what we are going to be doing is this. We want it to rotate the sun, but there is a force that is pulling it to the sun, and also the force or the gravitational force. Remember Newton's law of gravitation, where two objects are always attracting each other. Now these two forces are acting like that. So as it moves like that, it will be able to, the direction of the forces will change like that. So these forces are the ones that are keeping the object into balance like that. So with that said, that means to say we can equate the two, the centripetal force and the gravitational force. So we can be able to say, in this case, let's say ms is the mass of the sun, then me is the mass of the earth, then let's say r is the radius, which is the separating distance. So from the center of the earth to like that, so that is the radius, the separating distance. So now to derive, that means to say this force, the gravitational force and the centripetal force, because they are acting like that towards each other, they can be equated. So we are going to say the force of gravity, or rather the gravitational force, should be equal to the centripetal force like that. So therefore we know that Fg is equal to, we have, according to Newton's law of gravitation, it will be equal to m1 by m2. Now in this case we are going to use the mass of the earth times the mass of the sun, even if you interchange them it's okay, over the square of the radius like that. So then also the centripetal force, we know that it is equal to the mass velocity squared over the radius. Now which one is orbiting around the other is the one that will be contributing to this mass. So in this case it is the earth that is rotating around the sun, so this will be E like that. So therefore equating, we are going to get our GME ms over the radius squared should be equal to, we have the me like that, velocity squared over the r like that. So this will give us, we have me is common on both sides, so we can cancel it. If it's on the numerator we can cancel like that. So this is what we have for that. So we have our GMS like that should be equal to v squared, we have r squared, we have r. From here we are going to cross multiply, so it will be GMS times this r, it will be r, should be equal to v squared times the r, we have r squared. We divide r on both sides, r, this and this goes, this and this goes. So we are going to have GMS should be equal to v squared r. Now we're going to reach the t. Remember, we want t is directly proportional, t squared is directly proportional to the r to the cubed. So what we're going to do is that we know that, but we know that the angular, the velocity is equal to the r times the w, which is the angular velocity, which we discussed in another video. The angular velocity, we just multiply anything. If you are looking at distance, distance will be equal to r times its angular form. So this r is constant, so this is the angular velocity. But we also know that the angular velocity is equal to, we have the 2 pi, the angular velocity is equal to the angular displacement over time. The same formula, distance is equal to sorry, not distance, velocity, the same formula, or speed is equal to distance over time. So applies now the angular form. Now this angular form, if it's a circle, it makes a complete circle, which will be 2 pi. So the complete circle will be 2 pi. That's the displacement of the circle. So we are going to put our angular there. So the velocity will be equal to our r, then our w, we know that it is the angular over the period. So we have the velocity is equal to r, then we know that this the angular displacement, since it's a complete circle, it will be equal to 2 pi like that over the period. So the velocity is equal to 2 pi times r like that. This 2 pi times the r over the period like that. So this is our value. If that's the case, then we'll be able to say, our velocity is this. With our formula, we ended here. So we can say replacing, this formula. So where there is v, we are going to put this 2 pi r over t. So we have GMS should be equal to 2 pi r over t, then the square is affecting everything like that, then times our r. So this gives us our GMS should be equal to, we have our 2 squared, so we have 2 squared is 4, then this squared is affecting everything, so we have pi squared r squared like that over the period. Then we are going to have times our r like, so we have our r times our r like that. So this gives us our GMS should be equal to, then this t squared, so this will be t squared, this squared is affecting everything. So we have our 4 pi squared r to the cubed over the t squared like that. Then we are going to cross multiply like that. So this GMS times t squared, so we are going to have GMS t squared should be equal to 4 pi squared, this top part times 1, it will just be the top part. So 4 pi squared r to the cubed like that. Then we divide, we want to leave t squared alone, so we divide our ms, we divide by our ms like that. So our t squared is equal to 4 pi, we can write it like this, 4 pi squared over GMS like that. So times our r to the cubed, in fact times our r to the cubed like that. So as you can see, we have derived Kepler's law, because it is saying t squared is directly proportional to the cube of the radius like that. So this is basically how we derive. So we can say, if you are taught to derive, you can say therefore you can be able to say, therefore, the t squared is equal to, we are going to say that it will be equal to, we have not equal to, but is directly proportional to the r to the cube if you are asked to derive, because you are just looking at these two and they have the powers that are expected. So now it's not every time that you have to derive the equation. If you have forgotten the formula, you can derive. Now the approach is this: if the sun is in the middle, if it is the sun that is in the middle, we have the earth there. Whatever is revolving around will not show its value. As you can see, here it's the bigger one, which is our ms, because the mass of the earth was cancelled. Where was it cancelled? At first, here the mass of the earth was cancelled. The mass of the earth was cancelled. So the smaller one that is always orbiting is always cancelled. So now I'm going to give you a simple way of remembering this formula. You are going to be saying that the way to remember this formula, you are going to just be saying that, now let's imagine that you have the earth here, then the earth is being orbited by a satellite. So we have the mass of the satellite, we have the mass of the earth. So the formula will be the same as long as we have that. It will be t squared is equal to, we have 4 pi squared over our GME. You write the one that is being orbited by. So the bigger one is the one that remains. Then you have the r to the cubed. If the satellite is the one that is revolving around the earth, like that. So now how I can advise you to remember this is just say, you know that t squared is directly proportional to the r to the cubed. This is a standard. Then just say give me, so which is give me 4 pi's, like that. So this is the way. So t squared is equal to give me 4 pi's. 4 pi's. So depending, this value of ME will depend on which one. If it is the sun that is being orbited, the ME will be replaced by MS. So depending. So this is the formula we are going to be using instead of deriving every time. But if you forget, you can derive. But also knowing how to derive is very important, because they can ask you derive Kepler's law. So let's begin with this. Let's begin with this question as our first example. So for this one, we have calculate the mass of the sun using the fact that the period of the Earth's orbit around the sun is this, and its distance from the sun is this. So the distance is the radius. Immediately you just see anything, frequency, you see periods, just think of Kepler's third law. They have given you the period, then calculate the mass of the sun. Now remember, the sun is the bigger one, so it is the one that will be orbited. So we are going to say, using Kepler's law, t squared is equal to give me, now in this case, since it is the sun that is being orbited, so you will say, but that is the way of remembering, give me 4 pi's. So 4 pi's, then you have the r to the cubed. If you want to remember that pi is squared, just look at the periods there. So this is how you are going to find the mass of the sun. But you should know that the mass of the sun, the expected value, even as you are calculating, is 1.99 times 10 to the power 30, or just 2 times 10 to the power 30 kg. So you should get something like this. So what we are going to do is that we are going to say, let's make the mass of the sun the subject of the formula. So we are going to cross multiply. So this GMS times t squared, it will be t squared times GMS should be equal to, this times 1 doesn't change anything, so it will be 4 pi squared r to the cubed, like that. Then we make ms the subject of the formula, so we have g t squared over gt squared, like that. So this gives us ms should be equal to, we have the 4 pi squared r to the cubed over the gt squared. So the mass of the sun will be equal to 4 pi squared times what is our radius. So the radius is the separating distance. So in this case it is 1.4 according to the question. 1.496 times 10 to the power 96 times 10 to the power 11 meters. Then the radius is to the cubed. So make sure, so this is times, make sure that you deal with your calculator very accurately. That's the challenge. Then the gravitational force, we know that the value of the gravitational force is equal to 6.67 times 10 to the power negative 11. So this is what we are going to put for G. Well, 6.67 times 10 to the power negative 11 times the period squared. So the period is, we have our 3. So let me just write it here so that I can just lift it. So we have our 3.156 times 10 to the power 7. Make sure that it's in seconds. So we have this. Then we are going to put it times there. So doing that, but remember it is period squared. Period squared. So we have our 4 pi squared. Then we have our 1.496. Make sure that you put these in brackets while you are pressing on your calculator, then like that. So we have open brackets 1.496 times 10 to the power 11, then this value to the power of 3, like that. So we are going to have a value that will be equivalent to 3.35 times 10 to the power of 33 over the bottom part we are going to get. So we have 6.67. So put them in brackets. So open bracket 6.67 times 10 to the power of negative 11. You close the bracket. Then you multiply times, open the bracket, 3.156 times 10 to the power of 7 to the power 7. Close the bracket, square the value according to this square. So square the value. So this is, the bottom part is going to give you 66435.4412. Then divide. So put these in brackets, then divided by this. So we have our open brackets 4 pi squared times 3.35 times 10 to the power of 33. Close the bracket, divide. So the value it's giving me, just in case there are those that wants to be writing, it's on top, it's giving me 1.323 times 10 to the power 35 over our value of 66435.4412. So when we divided by, so 1.323 times 10 to the power of 35 divided by, so we put everything in bracket, then divided by 66435.4412. This is giving me 1.99 times 10 to the power 30 kg. So this is the expectation of the mass of the sun. If you are given to find the mass of the earth, your expectation should be somewhere 5.97 times 10 to the power 24 kg, like that. So with that said, we have found the mass of the sun as required. Let's move on to our next question. So if we have this, the International Space Station makes 15.65 revolutions per day. So immediately you see revolutions per day. So revolutions per day is frequency. Anything number per given time is frequency. But time per given number of revolution is period. So in this case, we have 15.65 revolutions per day in its orbit around the Earth. Assume that the orbit, assuming a circular orbit, how high is this satellite above the Earth's surface? So when we are doing such calculations, one thing that you need to know is that we calculate the radius of the Earth like this. So this will be the radius of the Earth. This will be the radius of the Earth. Then from that point, from this point, then we are going to also look at an extension to where the surface, to where the satellite is. So let's say the satellite is here. So this is the height. So they want this height. They want this height. Now you can't just solve it direct, but when we are doing our calculation, we follow the effective error, which is the error from the center of the Earth to where the object is, which is small r. So this small r is equal to the radius of the Earth plus the height. So using this formula, we can find the height by subtracting. But before that, we need to find this r because we can just find it direct. So what we are going to do is that, knowing fully that the period squared is equal to, we have, since as you can see, we have the Earth, then the Earth is being orbited by a small satellite, or rather a satellite. So what we will show in the equation is the bigger one, which is the Earth. So you will say, give me 4 pi's, then r to the cubed, like that. So this is the way to remember it. Now, what do we want to calculate? Now, one of the things that you need to know is that the mass of the Earth is equal to 5.97. They'll give you this value, but if they don't, you have to know it's 5.97 times 10 to the power of 24 kg. The radius of the Earth is 6.37 times 10 to the power of 6 meters. So now, which is the radius of the Earth, not that small r, but the radius of the Earth. So we'll use RE, radius of the Earth, like that. So first we need to find this r. We are going to use this r. We are using the radius from the center of the Earth to where the object is, not from the surface to where, like that. So this is not the radius of the Earth, but the radius combined from the surface of from the center of the Earth to the surface plus the extra height where the object is. So that's the radius. Remember, according to the law of gravitation, we are looking at the distance separating them, like that. So with that said, we are going to say, knowing that we have 15.65 revolutions per day, so we are going to convert this into revolutions per second. So if the day is, so all we have to change is the day. So using the changing conversion, if the day is down here, put the day up here. So 1 day is up here, so that this day and this day can go. But in 1 day, to maintain the meaning, there is exactly 24 hours. Likewise, the hour is down here, so that means to say you are going to put the hour up here. So 1 hour here. In 1 hour, there is exactly 60 minutes. Then you find that this and this end up going, then that means to say, get the minute now, since the minute is down here. So 1 minute, in 1 minute there is exactly 60 seconds. So this will give us, we have our, if you multiply everything, this minute and this minute will go, so it will be 15.65 revolutions per, if you multiply 24 times 60 times 60, 24 times 60 times 60, this will give us a value of 86,400 seconds. So then when you divide, it will be 15.65 divided by 86,400. This gives us a value of 1.811 times 10 to the power negative 4 revolutions per second. So this is frequency. So frequency is revolutions per second. So we are going to convert the frequency. In fact, it looks like friction. So we are going to convert the frequency into period. We know that The period is the inverse of the frequency. So this gives us the period to be equal to 1 over, what is our period? Or our frequency is 1.811 times 10 to the power negative 4, like that. Then we have revolutions per second. Now the way division works, as long as you have something also dividing another thing, the value that is the denominator for that one goes up. So we have the period should be equal to, so if you press 1 divided by, open the brackets, 1.811 times 10 to the power negative 4, we are going to get our value will be equal to 521.8 seconds. So these are the seconds. The second will go up like that. So this is the period. So knowing the period, what are we required to find? How high? So we need to find the radius first. So we are going to say the square of the period is equal to, give me 4 pi's. So give me 4 pi's r to the cubed. So we have the period. It is before that, let's make r the subject of a formula. So we are going to cross multiply. So this, the one that is having r is multiplying 1. So we have the 4 pi squared times r to the cubed is equal to give me t squared, like that. So this and this. So that is what we have. Then what we are going to have is, we are going to divide our 4 pi squared. We divide our 4 pi squared like that, so that our r to the cubed remains to be gme t squared over the 4 pi to the squared, like that. Then we want to get rid of this power, so we are going to say the cube root. So this gives us our value, r should be equal to the cube root of our gme t squared over our 4 pi squared. So this gives us our r should be equal to, we have the cube root of our value. What is our g? Our g, now we are replacing our g is, the gravitational force is 6.67 times 10 to the power negative 11 times the mass of the earth. I said it's 5.97 times 10 to the power of 24. So let's may reduce the font of this a bit. So reducing the font of this a bit so that we have enough space. So this is what we have, cube root, then times the period squared, and the period we have found it to be 5521.8. Then we square it, divided by our 4 pi squared. So our r should be equal to the cube root of our square root of, we are going to say 6.67 times our 10 to the power of negative 11. Then we multiply by 5.97 times 10 to the power of 24. Make sure that everything is in brackets, times our open brackets 5521.8 to the power of 2. So on top I'm getting a 1.214 times 10 to the power of 22. Then I divide over my 4 pi squared. So here the key term is just for you to be careful. So when we divide our top part, 1.2, make sure that it's in brackets, open brackets, 1.214 times 10 to the power of 22 divided by our 4, open brackets, 4 pi to the squared. This gives us a value that will be equivalent to 3.075 times 10 to the power of 20. Then find the cube root of this value. So the cube root of of our value of open brackets 3.075 times 10 to the power of 20. This gives us a value that will be equivalent to 6749657.047 like this. So this is the radius. Whichever radius you have found, it means it is the radius from the center here to where the satellite is. So that is the radius. So it is the radius from that point. Okay, let's do this. So that's the radius, that's the meaning, that's the radius you have found. R is equal to this. Now to find the height from the surface of the earth, that means from this surface to where it is, you are going to subtract. Now we are going to say R is formed by the radius of the earth plus the height, that is from the surface to there. So this is the height, then this is the radius of the earth. So we are going to have our radius, then this comes here, it will be minus the radius of the earth should be equal to h. Remember, the radius of the earth, we said the radius of the earth is 6.37 times 10 to the power of 6 meters. So we are going to have the radius, this radius is the effective radius, which is our value here. So we get this value and put it there, then subtract it with the radius of the earth. So just be careful with replacing. That's the key term to this topic. It's not that it's difficult, but it's very easy to make a mistake in your calculation. So make sure that you are very accurate. Press your numbers 2 times before you move on. Then our R is 6.37 times 10 to the power of 6 should be equal to h. So be putting them in brackets. You cannot put them in brackets if you want like this when you are showing your work, but on your calculator you should, so that it gives you your correct answer. So h is equal to, so when we have 6749657.047 minus, we open the bracket 6.37 times our 10 to the power of 6. This gives us a value that will be equivalent. We have this value 379,657.047 meters. So others can get a value such as 370, 379, 380, but the range, we are dealing with very big numbers, so there is a certain level of acceptability when they are marking. So this is our value. So this is the height there. So let's say we have an orbiting satellite stays over a certain spot on the equator of the rotating Earth. What is the altitude of the orbit? Called the geosynchronous orbit. So geosynchronous simply means to say the Earth, we know that the Earth rotates for 24 hours. So the Earth will be rotating for 24 hours. A geosynchronous orbit is if you have a satellite like that, it is also able to complete the rotation in 24 hours as well, so that at all points they are moving together. So if someone is looking at the satellite, they are here, they will be able to look at it like that. It will appear as if it's not moving, but the Earth is rotating. Let's say the Earth rotates and you are here. The Earth rotates and you are here. Okay, let's say the Earth rotates and you are here. Now, due to the fact that the sun does not move, it is there, then what happens is that the rays, for you it will be night, but due to the fact that also this satellite is moving, it will be seen at this point. So for you, relative to the satellite, you will feel as if, or see as if, the satellite is not moving, because you are seeing it throughout. If the Earth rotates and you are here, the satellite becomes here like that. So that is a geosynchronous satellite. It is one that completes its orbit for 24 hours. So now geosynchronous satellite, so that's that. But if it's another planet that orbits for 24 days, then that will be the geosynchronous orbit for that planet. But for the Earth, since the Earth rotates for 24 hours to complete its full rotation, even the satellite has to move around the Earth for 24 hours and return to its original position, so that the spot looks exactly the same point. So this question and this one are exactly the same, but I just wanted you to be exposed to the language they might just use the word geosynchronous orbit. So if this question, they are exactly the same, and 9 is the question we are going to solve, because they are going to produce the same answer, but 9 has got a B and this other one doesn't have a B. So therefore we are going to answer this one. But I just wanted you to know the language. From a telecommunication point of view, it's advantageous for satellites to remain at the same location relative to the location of the Earth. This can occur only if the satellite's orbital period is the same as the Earth's period of rotation, which is 24 hours. At what distance from the center of the Earth can the geosynchronous orbit be found? So they still want the distance. So what are we going to do? So the approach is the same. So looking at this, the approach will be exactly the same. So what is the distance from the center of the Earth to this geosynchronous orbit be found? Is it the same question for this one? What altitude? Altitude is the distance from the surface to where it is. So, and this one, at what distance from the center of the Earth can this okay, so these two questions are different, but I'll treat them as the same so that we don't waste time. So this one wants the distance from the center of the Earth, so they want the distance from the center of the Earth to where the satellite is. But this one wants altitude, meaning from the surface of the Earth to where it is. So let's begin with this one, A, then we are going to answer this one. So answering this one, we are going to say, at what distance from the center of the Earth can the geosynchronous orbit be found? So we are going to say t squared is equal to, we have give me 4 pi's, then we have the r to the cubed. What we are going to do is, we are making this r the subject of a formula. So we say cross multiply, it will be this multiplied by this, so it will be t squared times g me should be equal to 4 pi to the squared. Then we have r to the cubed. We divide our 4 pi to the squared, we divide our 4 pi to the squared. So this is what we have. So our r cubed, we can begin with r is equal to period squared, give me over, we have the 4 pi squared like that. Then we have the cube, we have the cube like that. We have the cube there. So this and this cancels, so we have our r should be equal to, we have the cube of our t squared, give me 4 pi like that. So we have our r should be equal to, now let's find the period. It's 24 hours, so convert 24 hours to seconds. So 24 hours times, the hour is up here, so you need to put it down here. So we have 1 hour. In 1 hour there is exactly 60 minutes. So that means this and this goes, then you multiply again. The minute is on top, so that means to say you want now the minutes to come down so that they can cancel. Then on top, in 1 minute there is exactly 60 seconds, so we have this. Then we are going to multiply, so we have our 24, we have our 24 times our 60 times our 60. This gives us our 86,400 seconds. So this will be our period. So if that is our period, then we are going to find our radius. Let me get the formula, the one we have made the subject of the formula of. So we have our r should be equal to, we have the cube of what is our period? Our period is 86,400. Then we have the squared times our g is equal to 6.67 times 10 to the power negative 11 times the mass of the earth, which is 5.97 times 10 to the power of 24 kg, like that. Then divide this by your 4 pi squared, like that. So pressing on our calculator, we have r should be equal to, we have 86,000, so we square this. When we square this, we have the value of so let's multiply everything. So make sure that everything is put in brackets. So 6.67 times 10 to the power of negative 11, like that, times the 5.97 times 10 to the power of so mass of the earth, 5.97 times 10 to the power of 24. So after we do that, we are going to get a 2.973 times 10 to the power of 24 over the 4 pi squared. So let's put in everything in brackets. So open brackets, 2.973 times 10 to the power of 24. Then we divide this, divided by open brackets 4 pi squared. We are going to get our r should be equal to the cube root of, I'm getting a 7.53 times 10 to the power of 22. Then find the cube root of this value. So the cube root of open brackets 7.53 times 10 to the power of 22. So this gives us a value that will be equivalent to 42227787.3. So this will be our radius. So this is the answer to this question. At what distance from the center? So this r that we find is from the center of the earth. So that's the answer. Then for this other one, which says that what is the altitude? Altitude is the distance from the surface to where an object is. So that is altitude. So we are going to say, to answer this one, we are going to say r is equal to, we have our radius of the earth plus h. This comes here, we are going to have r should be minus re is equal to h, which is, in this case, it is altitude. So this altitude is equivalent to, we are going to say this radius we have found is 4222787.3 meters minus the radius of the earth is 6.37 times 10 to the power 6, which should be equal to the h. So the h is equal to, so when we subtract this minus our open bracket 6.37 times 10 to the power of 6, this gives us a value of 358,5787.3 meters. So this is our value, like that. If that's the case, for B of this one, says what is the orbital speed? So remember, we derived the speeds to be 2 pi r over the period. So to find 2 pi r over the period, we are going to say, let's make the, we have everything. So we have V should be equal to 2 pi then this radius is from the center. Don't get it confused. So it is our 4, it was 4222, okay, orbital speed 4222 7787 7787.3 divided by the period it's taken. We found it to be, is it 86,400 seconds. So this gives us open brackets 2 pi times 4,222,787.3 close brackets, divide our 86,400. This gives us a 3070.89 meters per second. So this is the orbital speed, like that. So that's that for this question. So we are remaining with how many questions of this type? So we have answered this one. We are yet to answer this one, and we have answered, which other one have we answered? We have not answered this one. We have not also answered, we have answered this one. We have not answered this one. Yeah, so we are just basically remaining with 3 questions. Is it only 3 questions? Yeah, so let's answer this one. Other example, using this one as our example, we are going to have, so we have, for a satellite to be in a circular orbit 780 kilometers above the surface of the Earth, what is the orbital speed? What orbital speed must it be given, and what is the period of the orbit? So same approach, the orbital speed, what is the orbital speed that it must be given, and what is the period of the orbit? So we are going to say, remember, if as long as we have the Earth, we have another rotation, we can equate the centripetal force to be equal to the force of the gravitational force. So the one that is causing there to be a centripetal force is the attraction forces by the gravitational force. Knowing that the centripetal force is equal to the one that is orbiting is the satellite, so we are going to say m sub s, which is the mass of the satellite. We know that the centripetal force is equal to mv squared over r, so we are going to say mv squared over the r should be equal to, we are going to have, what is our fg? So this fg is given by mass g, that by the mass 1, which is, in this case, it will be the mass of the Earth times the mass of what? Times the mass of the satellite over the r squared. So this is fg is equal to g m1 m2 over r squared. So as you can see, this and this are the same, and they are both numerators, so you can cancel them. So we are remaining with our v squared is equal, v squared over r is equal to gme over r squared. So we are going to cross multiply. So this times this, it will be v squared r squared is equal to gme times r. To leave v alone, we say r squared over r squared, so that this becomes this and this goes, so this becomes v squared is equal to gme over the r, like that. So this is our formula. So let's find the square root so that this and this can go, so that we have v is equal to the square root of our gme over the r, like that. From here, just replace. So just replacing, we are going to have, Now be careful, this r is the distance from the center of the earth to where it is. They have given us everything, so we use them. So this r is the, they have given us that it is 780 kilometers. So from the center of the earth to here, it is 6.37 times 10 to the power of 6 meters. Then from here up to there, it is 780 kilometer, like that. So you add, so your r will be equal to 6.37 times 10 to the power 6 meters plus the 780. We know that kilo is a unit of 10 to the power 3. So 10 to the power 3 meters. So this gives us r is equal to, we have 6.37 times 10 to the power of 6, like that. We add plus open brackets 780 times 10 to the power of 3. So this gives us a value of 7, 1, 5 and 4 zeros, like this. So 7 million, and yeah, so this is the value, 7.15 million. So this is basically what we have. So this is what we are going to replace in our equation. So getting this equation and putting everything, we are going to get a value that will be equivalent to, we have our V should be equal to, so our G value is equal to, we have 6.67 times 10 to the power of negative 11 times the mass of the earth is 6.3, mass of the earth is 5.97 times 10 to the power of 24 kg over the radius, which is 7150, like this, which we have found. So our V should be equal to, so on top, when we do our calculation, 6.67 times 10 to the power of negative 11 times our 5.97 times 10 to the power of 24. This gives us our square root of our 3.98199 times 10 to the power of 14 over, we have 7150123. So V is equal to the square root. So we divide the square root. So the one on top, 3.98199 divided multiplied by 10 to the power of we have 14. 10 to the power of 14 divided by open brackets 77150, 4 zeros, like that. We are going to have the square root of 55692,167.83. So our V should be equal